Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem, most profitable path in a tree. And as long as the problem description is, the solution is going to be even longer. It's tricky to come up with. I'm not going to lie, to come up with the solution to this problem is a little tricky dicky, but it's very interesting. It's very useful. I think you'll learn a lot from that part of this problem. Then in terms of coding it up, it took me about 40 lines of code to code this up, and provided I'm using Python, a very nice language for these types of problems. And from reading the problem to like fully implementing it and passing it on Leetcode, it took me like 30 minutes, but I think that's a little bit misleading. Like this problem is very hard. I even had a bug when I ran my submission. So like this is one of those problems where if you get it in a real coding interview, hopefully you're not expected to solve it in like 20 minutes. Hopefully they give you at least 45 minutes, maybe some hints, something like that. I don't know. But let's go ahead and get into it. Let's mostly focus on this picture over here. There's a lot of words going on. Let's focus on the example. So the idea is that we have two people. Let's call them A and B, Alice and Bob. Alice is always going to start in this graph at node 0. So this graph is an undirected graph, but it's also a tree. So that specifically means that there is not going to be a cycle in this graph. Very important to recognize that because I don't think they explicitly mention that. So again, we're given this graph. It's really a tree that's given in the form of a graph. We're given like the edges. Of course, we're going to have to probably convert that into something that's easier for us to traverse. I'm going to convert that into an adjacency list. So just kind of telling you that up front because that's kind of the easy part of this problem. So like I said, Alice always starts at node 0. The nodes are going to be numbered from 0 to n minus 1. And it's going to be a connected graph. That's kind of implied by the fact that it's a tree. And Bob is going to be starting at whatever the parameter happens to be. We're given a parameter for the starting point of Bob. In this case, it happens to be at node 3. So Bob is going to be over here. Now, I'm going to finish reading the rest of this problem. I'm going to explain to you the intuition behind the solution. Then I'm probably going to try to do a bit of a dry run, and then I'm going to code up the solution for you and also give you like the big O runtime and all that. But one thing I will say is in the past, sometimes I tried to explain these problems by really walking you guys through the exact thought process I had when I was coming up with the solution. And in the past, to be honest, I've learned that most people actually aren't looking for that. People say they are, but I've recorded videos where I kind of went on like some tangents for like a few minutes, and then I've gotten comments that people said, you spent a bunch of time talking about a bunch of things that did not explain how the solution works, and that felt like a distraction to a lot of people. So I'm just going to try to do the best that I can. It's not as clear what that exactly is. You know, you can't always make everybody happy, but I hope that most people will at least understand what the solution is by the end of this video. So in all of this, we're kind of given some rules of the game, sort of the simulation that we kind of want to run. And at the end of that simulation, we want to figure out what is the max profit that Alice can have. We don't really care about Bob. We want to know what's the max profit Alice can have. And that's actually a bit more straightforward than you think. The rules of this game are in some sense meant to confuse you. Let me kind of cut through all the verbosity of this description and tell you what this problem is really saying. Each of these nodes has, of course, the label, but it has a value here. It's in black, so you can't really see it super clearly. That's kind of Leetcode's fault because I'm in dark mode, but anyways. This is a -2, this is a 4, this is a 2, -4, and a +6. So each of these values represents the total income, or I like to call it the profit that we can get from each node. In some cases, it's going to be negative. In some cases, it's going to be positive. It doesn't really matter whether it's negative or positive. Like the solution isn't really going to change based on that. And so what we want to do is have Alice traverse the tree such that she keeps moving down until she reaches a leaf node. So in this case, she really doesn't have any choices. She has to go to node 1, but then she has a choice. She could either go to node 2, in which case she reaches a leaf node, nowhere to go from there, and then she will stop. She's never going to move back up to a previous node. Or she could have gone the other way. She could have gone this way where Bob happens to have started, and then she could have taken this node, and then she could have taken this node. There weren't really any choices from here. She had to go there. Maybe there could have been a choice. There could have been another node over here, but in this example, there's not. It's a pretty simple example. So in this case, she will end up here at this leaf node. And so as Alice goes, she's going to be collecting the profit of every node that she visits. But there's going to be a catch, and I'll tell you that in just a bit. So that's Alice's perspective. Now, Bob is kind of in the opposite situation. We don't really know where he starts. He could start at a leaf node. He could start somewhere else. He's definitely not going to start at node 0. That's actually given to us in the constraints. So Bob and Alice will not have the same starting point. That's pretty good. That's convenient for us. But Bob, in some ways, his options are actually limited because his goal is to reach the root node, which is where Alice started at node 0. So Bob is never going to have any choices because remember, we do not have a cycle. So here, from Bob's perspective, there's only one choice. He has to move in this direction. You could think, okay, well, what if there was another node connected to Bob, like over here? Sure, maybe Bob could have moved there, but do you see how that's just a leaf node? Or even if it wasn't a leaf node, eventually it would lead to a leaf node. That's not the direction Bob wants to go. Well, now you're probably thinking, okay, but what if that node was connected to the root somehow? Well, now you see you got a cycle, so that's not possible. So you got to have a bit of a deep understanding of how trees work. If you don't, I encourage you to maybe check out some of the resources on Leetcode.io. Some of the courses might be useful for you, but this kind of knowledge is definitely required for solving problems of this difficulty. But anyway, so now continuing, we know that there's only one choice for Bob. It's not going to be straightforward for us to figure out what that is. Like we're here, Bob could have 10 different edges coming out of it. We don't know which one is going to lead to this node, but we know Bob's situation is very simple. Bob does not have choices. No choices available for Bob. He has to go in this path. Alice is the one that has choices. Anyways, so Bob's simulation is going to be very simple. Bob is here, then he's going to take this node, and then he's going to take this node. And Bob is going to do the same thing. He's going to take the profit or income of every single node. We don't really need to keep track of how much Bob collects because we're not going to return that. We don't really care about that. But it's going to be important which nodes Bob visits. It's going to be important to know which nodes Bob does collect from because in this problem, they say this. Like, let's say I started here and Bob's over here. Alice is going to take this profit, Bob is going to take this profit, and suppose now Alice is here. And then Bob is at the same position. Bob is here as well. Well, if they land on the node at the exact same time, so let's keep track of the time as we run this simulation. So if they land on the same node at the same time, they're going to take the profit or even the loss and divide it between the two. And we're guaranteed that these are always going to be even numbers. So it's going to be easy for us to divide those by 2. The return value is going to be expected to be an integer regardless. Now, also, it's true that if Alice lands on a node, suppose Alice was here and Bob, they share the profit, and then Alice ends up over here, she visits a node that Bob's already taken from. Well, then Alice cannot take anything from this node. She's going to get a profit of 0 from that node. Or maybe if there was a loss from that node, she's still going to have a loss of 0 from that node. Bob already visited it. He already took everything. Alice has nothing left. But then maybe Alice will then visit this node, which nobody has visited. Bob didn't visit it yet, so she can take all of the profit. So those, I believe, are the main ideas from this problem description. I'm just going to kind of skim over this just to make sure I didn't miss anything. But again, what we mainly want to do is return the max possible income Alice could have if she travels to the optimal leaf node. So regardless of any of the paths that Alice takes, we want to run the simulation such that she maximizes her profit. So I don't know about you guys, but as soon as I hear that, my brain starts thinking. I start thinking, crap, is this going to be a backtracking problem? Because it looks like it's going to be a pain in the ass to code up if it's backtracking, to be honest. Okay, maybe not. Maybe it's going to be a greedy problem. If it's a greedy problem, we're probably going to need to figure out some tricks, maybe make some key observations about this problem, or maybe it's dynamic programming, which I feel like for this type of problem on a graph, that's also going to be a major pain in the ass. So when I looked at these 3 options, I thought, man, I pray to God that it's a greedy solution. And then I looked at the constraints of the problem and I saw that n, the max value of it could be roughly a 10 to the power of 5. So that told me it's probably not backtracking and it might be dynamic programming, but I'm going to try the greedy solution first because I assume that that one's going to be a bit easier. even though it is a bit easier, like I said, it's still going to be like 40 lines of code in Python. So yeah, and it did turn out to be greedy, by the way. So now let's start to make some observations about this problem. Believe it or not, the most important observations I actually already made for you. These are the observations. Alice has choices, but Bob does not have choices. So the fact that Bob does not have choices, maybe we can just run the simulation from Bob's perspective. We already know somehow we can figure out the exact nodes that Bob is going to visit. And after we've determined that and we've computed that, can we then run the simulation from Alice's perspective to then try to maximize the amount that she can collect? And the answer is yes. But the question is, how do we do it given the way that we want to run the simulation and the rules of this game that they've given us? Well, one thing that was kind of interesting to me is even though Alice has choices, the traversal from Alice's perspective is actually easier. Like from here, we're just kind of going down and it's pretty easy to figure out how to do that. Just don't visit like the node that we came from. There's not going to be any cycles or anything like that. But Bob's perspective is a bit different. Even though he doesn't have choices, we have no idea which direction to go. I mean, which direction is going to take us to the root? The thing that I realized was maybe the easiest way to figure that out is just to kind of brute force this. Not literally brute force it, because we could do a traversal from starting here, going in every direction just by visiting every single node a single time. And then among all of those paths that we take, so starting from here, we could possibly take this path. We see, okay, well, that was not the root node. That did not lead us to the root node. Okay, well, we could then go over here, take this node, and then maybe the next decision we try is to go down here. Well, once again, we realize that did not take us to the root node. Okay, well, we still have some options. From here, we could go up, and there you go. We reached the root node. So these are the nodes that we want to say that Bob is going to visit. And if you see what I just did on this picture, didn't that look like a depth first search? Yes, that's exactly what it is. Now, there are other traversals that you could do. The one that just felt the most intuitive to me was a DFS. I think that's the easiest way to actually code this up as well. But now, in terms of marking Bob's nodes visited, what do we actually care about? Like, we don't necessarily know that Bob is going to be able to collect the profit from every node that Bob is able to visit. In this case, Bob visits this, and this, and this. We have no idea when Alice is going to visit these nodes, if Alice is going to visit any of these nodes. And based on that, we don't know how much profit Alice is going to be able to collect. For us to determine how much profit she could collect, what we should really be doing is tracking the time that Bob visits each of these nodes. Because then when we run the simulation from Alice's perspective, we can also keep track of the time. And then as we visit nodes, we will be able to determine, was Alice at this node first or did Bob visit the node first? Because if Bob visited it, then we should not be able to collect the profit. Or maybe they visited the node at the same time, in which case we have to divide the profit by 2. Or maybe Alice visited the node first before Bob got there, so Alice can take all of the profit. And the last case would be maybe Alice is visiting a node that Bob never ended up visiting. Maybe it would be this node, in which case, again, Alice just takes all of the profit. So I hope that makes sense to you. I don't think it's crazy complicated. It might not be obvious. It's not crazy complicated, but yeah, implementing all these little things is going to be a pain. And by the way I'm going to track that is probably by using like a hash map for every single node. For Bob, we kind of throw it into a hash map and just mark the time. So let's do that. Let's say for a node 3, we visit it at time 0. For node 1, we visit it at time 1. And for node 0, we visit it at time 2. You can kind of see that this probably could have been implemented with a BFS as well, but I feel like it would have been harder to do that. So I just stuck with DFS. Okay, now I'll use a different color for Alice. So Alice is starting here at 0. And for Alice, the difficult thing is that we do have choices. So we really have to kind of try every single path to figure out which one would have been the best one. I think that's also possible to implement with DFS. We could kind of go through every single path, figure out which one led to the maximal result. But I think it's also possible to do it with BFS. That's the one that came more naturally to me, but I didn't actually implement the code for the other one. Maybe the DFS one actually resulted in a cleaner solution, but I thought BFS was fine. So BFS will work like this, where we will start here and we will make both choices at the same time, or maybe we'll have 3 choices. We'll make every choice at the same time. So we start here, and let me actually mark the times for Bob. So let's say this was 0, this was 1, and this was 2 for Bob. So now I'm here at time 0 with Alice, and I see my time was less than Bob's time, so I take all the profit. I get that -2. Great. And then I'm going to make every choice that I can. I only have one choice, so I go there. And then I reach this node at time 1. Okay, it's a +4. Looks like Bob reached that node at the same time that I did. So I have to divide that profit, which is 4, and then it will be 2. So I'll add a +2 here to the total profit that I have so far. Now I make these 2 choices at the same time. I could either be at this node at time 2, or I could be at this node at time 2. If I take this node, I will get a profit of +2. If I take this node, I won't get anything because Bob reached that node first. So even though I'm drawing the total profit over here, what we're actually going to be doing is for each node keeping track of the profit we have so far. So here we had like -2. Here we got a +1 or +4. We divided that by 2. So then we ended up with a total profit of 0. When we get to this node, we got the +2. So we end up with a total profit of 2. I'll put the colors in green just to indicate that it's a profit. So here, +2. And then here, what we could have gotten is nothing. So we would have had a total profit of 0. And then we would have finally, for Alice, visited this node at time 3. And it looks like nobody visited that node so far. It has a profit of 6. So our profit previously was 0. So we can take that 6 and collect all of it. So now at this node, we'll have a total profit of 6. Now, among all of the leaf nodes, there were only 2 leaf nodes. This one over here and this one over here. We reached them at different times. This leaf node was reached at time 2. This leaf node was reached at time 3. This one had a profit of 2. This one had a profit of 6. The maximal is, of course, 6. So we return the value 6. On this picture, I hope the solution did make at least some sense. I encourage you to try to draw it out yourself if it didn't. Or if you didn't like my choice of DFS or BFS, you can try to code it up using your algorithms of choice. But I'm going to go ahead and code this up now. And you can see that we're basically just running a traversal on the graph twice. So the total time complexity is going to be big O of n, and that's similarly going to be the space complexity as well. If you have any interest in seeing my original thought process when solving this problem, this is what it is. But just keep in mind, I didn't actually write these notes from top to bottom. I kind of filled them in randomly. That's kind of how my brain works, but I will reset this. And so the first thing we're going to do is just build the adjacency list from the edges that were given. Pretty easy to do that. I've done it a million times. I won't go super in depth. I'm going to use a default dictionary, the default value of a list. I'm going to go through every edge, unpack the 2 nodes. The edges are going to be directed, so I can do this. Adjacency of v1, add a neighbor v2 for it. And similarly for v2, add a neighbor of v1. Then we're going to do the DFS Bob simulation. So I'm going to say Bob time is going to be the hash map, or Bob nodes time. Either way, this is what it represents. It's a little hash map. It's going to map every node that Bob visits to the time that it was visited. Then I'm going to implement a little DFS to handle that. Now, you might think that we need a visit hash set to make sure that we don't get stuck in a cycle using this DFS, but actually recognize that we're given a tree as the input. So it's actually even easier to not have a cycle. We can do that by having a source node and also keeping track of what the current node's parent was. Also, let's keep track of the current time that it took us to reach this source node. So the way this DFS is going to be called is like this. We're going to say DFS starting from the node that Bob starts at. And let's just say its parent is -1 because it doesn't have a parent right now. The parent is just used to indicate like the previous node, I guess. And so maybe a better name for it would be previous. We just don't want to get in a cycle where we go from the source node back to the previous node, back to the source node, etc., etc. And we can start at time 0. Okay, so in terms of the base case, we know that the main one is when the source is equal to 0. That's very good. We can return from that, and we're going to return true to indicate that this was the path that led us to the root node. But before we return, let's also mark the time that it took to reach this node. The node is 0, or we could also just use source, and this was the time it took to reach it. Now we can do this. If the base case did not execute, we will go through the neighbors of the current node. So neighbor of source, the adjacency list. And if this neighbor is the previous node, we definitely want to skip it, so we can just put a continue statement here. Otherwise, we do the recursive case. We call DFS on the neighbor, and we say, okay, the previous node was the current source node, and we say, okay, the time to reach that neighbor is going to be the current time plus 1. And what we want to know is the return value of this function call, because if it was true, then that means that the current node, the current source node, is along the path that it takes for us to reach the root node. And so if that's the case, we can say, okay, for the current node as well, take it, the source node, and say, okay, this was the time for us to reach that node. It is along the path to the root. So maybe to make that more clear here, I can say node on root path. And from here as well, we want to propagate that return value of true. So we can do this, return true. And outside of that, we can return false if this never executes. So this part, I believe, isn't too bad, but I mean, this on its own is kind of a Leetcode medium, if you ask me, or maybe it's close to that at least. But anyways, let's continue. That was the Bob simulation. We call DFS, so we expect that this is going to be populated after that. And now it's time for the more interesting part, the Alice simulation, which I'm going to do with a BFS. So there's many ways to code this up. I'm really going to take advantage of the fact that Python gives us some things. So I'm going to have a queue, and it's going to be a double-ended queue. And so I'm going to initialize it with this. It's going to be initialized with a tuple of 4 different values. Let me comment what those are. It's going to be the node that we're currently at, the time it took to reach that node, the parent, or you could say the previous node, so that we don't get stuck in a cycle, and the total profit along the path to get to that node. So we know that the starting point of Alice is always going to be 0, so that's pretty easy to fill in. The next thing is the time. Well, we're starting at time 0. The parent of the root node, it doesn't really have a parent, so we can just say -1. And the total profit along the path to get to this node, including that node. Well, that's pretty easy. And I didn't really talk about this, but we're given a parameter called amount. It's an array. It tells us for every node, what's the profit of that node. So we can start here by just saying we have the amount of node 0. We know that we're dealing with negative values sometimes, so I'm going to actually initialize my result to not be 0, but to be float of -infinity, basically the smallest value you can have in Python. And eventually we're going to try to increase this, and after that, we're going to end up returning it. So now this is going to be kind of similar to like a textbook BFS with a small differences. So I'm going to say while the queue is non-empty, I'm going to pop from the queue and I'm going to get 4 values. That's a lot of values to get. We're going to get the node, we're going to get the time, we're going to get the parent, and we're going to get the profit. And then we're going to do the BFS part. We're going to go through all the neighbors of this node. So like this. And the easy thing is if this neighbor is equal to our parent, well, then once again, we just kind of continue, pretty similar to what we did in the DFS over here. But otherwise, what we're going to say is, okay, the profit of the neighbor is this. At least this is how I like to code it up. I try to make it as simple as possible, at least for myself. I don't know what your opinion is going to be on this code, but here I say the neighbor's profit is this. We assume that we can collect all of the amount from the current neighbor, but we don't know if that's actually true. So what we're going to do is have a couple of conditions. We're going to say if the neighbor is in Bob time, I think that's what the hash map was called, Bob times. If that's the case, well, then we need to know, does Bob reach this node first? Because if he does, well, then that's going to mean this. Our current time to reach this node was this, so the time to reach the neighbor is going to be time plus 1. But maybe Bob's time was even less than that, meaning our time is greater than Bob times of this neighbor node. And if that's the case, then we have to take that net profit or neighbor profit and set it down to 0. Because we won't be able to collect any of that. Bob reached it first. Or maybe it's the other case where actually time plus 1, the time to reach this neighbor, maybe I could have put that into a variable. Maybe I should actually to make this more readable. Let's do that. Neighbor time is going to be time plus 1. So let's do that. And then neighbor time over here, if that's equal to Bob times of the neighbor, well, then they have to divide the profit. Then that means Alice is only going to get half of that. So we can set neighbor profit equal to the neighbor profit divided by 2. Okay, so this is pretty nice. This is a very nice way to deal with figuring out how much profit Alice is actually going to get from the current neighbor node. But now, how do we update our queue? Well, that's actually not too bad. We can do this. Queue.append a big fat tuple. And if you forget what values we had, that's kind of why I put the comment up there. It's going to be the node, so the neighbor, the time, which is neighbor time, the parent, which is going to be the previous node, so that's just going to be the original node, and the total profit. Well, the total profit to get to this node was this profit, and to that we can add the neighbor profit like this. So that's what we append to the queue. Now, there's only one thing left, and I like to give you guys a challenge, so I'll let you try to figure out what to do or how to do it. When do we update our result? How do we only update the result for leaf nodes? Because of course, over here, I could just say, okay, set result equal to the max of result as well as the profit of this node. But there's no guarantee that this node is a leaf node. So how do we do that? Well, what's so special about a leaf node in a tree? Leaf nodes only have one edge connecting them to another node. So maybe I could put an if statement like this: if length of the adjacency list of the current node, if the length of it is equal to 1, it only has one neighbor, so surely it's going to be a leaf node, right? Maybe I could do something like this, but that's not quite correct either, because that would end up including the root node, which is 0. Maybe the root node only has one neighbor as well. So actually, one way to handle this would be to disclude the root node, or what I like to do is actually just take this code and only apply it to the neighbor. So I'm just going to put that down here. And so then instead of using the node, I will use the neighbor. And instead of using the profit, I'll use the total profit over here. So this will ensure that we only apply this condition for leaf nodes. So we only consider the profit of leaf nodes, the total profit, that is. So now you can see my entire code. We reached line 44 over here, but I did have several comments and a lot of spaces. I'm trying to fit this all on the screen at one time. I don't know if that's going to be possible. Anyways, here is the Alice BFS portion of the code, and up above is the Bob DFS portion of the code. Of course, I had a typo. I used Bob nodes instead of Bob times. But other than that, it seems like our solution was correct. It was pretty efficient. If you found this helpful, definitely check out Leetcode.io for a lot more. It supports me a lot. Thanks for watching, and I'll see you soon.